This microwave window is full of holes. You can see through it, yet it strongly attenuates the oven's microwave field. The black color is not the trick, and too big for the holes is only the start. The answer is a conductive screen inside a complete door. Visible light and microwave energy are both electromagnetic waves, but this door sees a huge difference in scale. The same perforated conductor can pass enough of one for us to see, while strongly attenuating the other. A home oven operates near 2.45 GHz. Wavelength is light speed divided by frequency. At that band center, the free space wavelength is about 0.122 meters, 12.2 centimeters. That is the scale this grid must manage. Now, the mechanism. Treat an opening in the conductive screen as a very short waveguide. Conducting boundaries determine which field patterns can propagate efficiently. At the oven's frequency, that opening is below cutoff. Much of the microwave field reflects, and the field that enters decays sharply through the aperture. It does not become mathematically non-existent at the first edge. Visible light wavelengths are vastly shorter. At that scale, the openings are not deeply sub-wavelength in the same way, so enough light can propagate through for an image to reach your eyes. The grid remains visibly transparent without becoming a large opening at the microwave scale. Visible light is typically about 380 to 700 nanometers. Put that beside 12.2 centimeters, and the common oven band wavelength is roughly 175,000 to 322,000 times longer. That ratio is not a leakage calculation. It explains why one opening occupies radically different scales for the two waves. So the microwaves are too big to fit is useful but incomplete. Electromagnetic fields are not beads hitting a strainer, and smaller than the wavelength is not a universal blocking rule. Material, aperture shape, spacing, thickness, seams, and frequency all affect what happens. Same holes, different ratio. To visible light, the grid remains an optical path. To a roughly 12 centimeter microwave field, it behaves much more like a continuous conductor. Its geometry responds differently at two radically different wavelength scales. Now the complication: the viewing screen is only one layer. A real oven also has a perimeter, seams, alignment, and moving hardware. FDA manufacturer documentation treats the viewing screen and door sealing system as separate design concerns. So the mesh makes the oven safe, leaves out most of the assembly. Build the system layer by layer. The metal cavity helps contain and reflect the field. The conductive screen handles the viewing opening. The perimeter uses a model-specific radio frequency interface. Some documented designs use a choke, but that is not universal. Latches preserve the intended alignment. Then, interlocks stop microwave generation when the door opens. Each component handles a different failure path. Under the current US performance standard, an oven must have at least 2 operative safety interlocks. A single mechanical or electrical component failure cannot make all of them inoperative. The standard also requires monitoring, designed to make the oven inoperable after a monitored interlock failure. That is redundancy. The screen attenuates the field during operation. The interlock system addresses access to the energized cavity. The regulation also reveals an important nuance. It does not promise mathematically zero emission. For the complete oven, The US ceiling is 1 milliwatt per square centimeter before acquisition by a purchaser and 5 afterward, measured at points at least 5 centimeters from the exterior. Those are product compliance maximums under defined conditions, not typical leakage, not a general human exposure limit, and not a do-it-yourself pass or fail number. That complete oven requirement does not prescribe one universal screen hole size. Change the aperture's shape, longest dimension, pitch, thickness, conductivity, seams, frequency, or resonances, and attenuation can change. Household ovens operate near 2.45 GHz, but that is not one exact frequency for every microwave system. Even the screen's material and perimeter seal design can vary by model. This is also why putting a phone inside, watching a Wi-Fi connection, or waving a cheap meter around cannot certify that an oven complies. Frequencies, instrument response, load, distance, and test conditions differ. We do not need to power an empty or damaged oven, defeat a latch, or probe an interlock to demonstrate the physics. The scale and conductive geometry already supply a safe visual proof. Here is what we can prove safely. With the oven intact and unplugged, rack focus through the conductive pattern to an original high-contrast card. Then compare the grid with the original wavelength scale animation. This proves visibility and illustrates scale. It is not an emissions test. No exact aperture number belongs on screen unless that door has been measured with a documented calibration method. The practical safety boundary is simple. FDA says not to use an oven whose door will not close firmly, or is bent, warped, or otherwise damaged, and to stop immediately if it operates with the door open. A visual check cannot certify emissions. Contact the manufacturer or qualified service personnel. Never remove the cabinet. Dangerous electrical hazards can remain even after unplugging. So why can you see through a microwave door? Because a hole means very little without wavelength and material. Conductive millimeter scale openings strongly attenuate the oven's roughly 12 centimeter microwave field, while much shorter, visible light passes. That lets you watch the food without making the window a large microwave opening, and the cavity, door interface, latches, and interlocks complete the safety system. And that raises the next hidden door question. Why does a conventional oven door need multiple layers of glass? They may look redundant until you trace what the complete door has to do.